Hello, my name is Shahab Salim and I would like to welcome you today to this presentation on the experimental and numerical study of the Aero acoustics of flow over structured sheet metals. This work has been done in cooperation between the Technical University of Liberec and the Technical University of Brandenburg in Cottbus. This presentation starts by an introduction to the topic of Aero acoustics. Then I will present the objectives of this work. After that, I will present the experiment and its setup, as well as the definition of the numerical simulation. Then, I will be presenting the results of the two approaches, comparing between them, and finally, I conclude the outcomes of this work. As you may know, sound is nothing but a pressure wave that flows in a medium due to the subsequent vibration of its particles. This pressure wave is generated when a sound source creates a pressure change in the medium, and depending on the kind of the sound source, we may classify sound into mechanically generated or aerodynamically generated sound. Mechanically generated sound is the sound that is created due to the vibration of a solid body. This vibration causes the surrounding medium particles to vibrate in return, creating the pressure wave. On the other hand, aerodynamically generated sound is the sound that is generated when a flow is intercepted by a body or a cavity. This interception creates the pressure change in the flow, which may later turn into a pressure wave. And needless to say that the generated sound would mainly depend on the geometry of the intercepting body. The objective of this work is to study the aeroacoustic noise that is generated when air flows across sheet metals structured with periodic hills. The study considered inlet airspeed of 18 meters per second, and it has addressed three different hill geometries named as KMT, that has the shape of a star, or PVO, that had the shape of a dome or a bubble, and finally the VAB, which has the shape of a hexagon. Each of these geometries was defined by two parameters, the hill height, C, and the hill size, G. As we can see here, PVO had the smallest hill height as well as the smallest hill size, while the VAB had the biggest hill height and the biggest hill size. In this work, all the sheets were cut into the same outer dimensions, where it had chord of 300 millimeters in length over the direction of the flow, and it had a width of 200 millimeters. The dimensions of the hills can be represented in a non-dimensional form using the ratios between the chord and the hill height, as seen here, and the ratio between the hill size and the hill height, as can be seen here. Finally, the airflow of 18 meters per second would have Reynolds number that is estimated based on the hill height, as we can see in this column, and as we can see for the PVO sheet, it had the minimum Reynolds number of 1800s, while the VAB had the highest Reynolds number of 4200s, of course according to the hill height. The experiment has used a wind tunnel. The wind tunnel had a test section of 50 centimeters in length and 20 centimeters in width and 15 centimeters in height, connected to an axial ventilator of a controllable rotational speed. The test section had the metal sheets placed at exactly the mid height of the section. With that wind tunnel, a Brolankayer 2250 microphone was used to record the generated sound, as well as moreover a hot wire anemometer with the data logger was used to record the instantaneous speed of airflow above the sheet. As we can see here, the velocity has been measured at 4 points, P1, P2, P3, P4, situated at 10, 20, 30, and 40 millimeters respectively from the midpoint of the trailing edge of the sheet, where flow flows in this direction. Moreover, Sound has been recorded at the point PM, which lies outside of the test section at its higher surface, where it is at a distance of 75 millimeters from the sheet. It's important to point out that in this experiment, the involved sound included two effects: the effect of the sound that's coming from the axial ventilator, which was quite loud, as well as the sound that's coming from the flow across the sheets. Therefore, it was important to differentiate between the two effects, and to do so, it was necessary to perform the measurements, the sound measurements, twice. Once without the sheet being inside, and in this case we are measuring the effect of the axial ventilator, and then we repeat it again by placing the sheet inside, and in this case we are measuring the effect of the two effects together. And in order to be more sure about the nature of the sound that's being measured, an acoustic camera has been used and directed towards the test section. By doing so, we would be able to identify the location of the sound production. The acoustic camera was used in the two measurements, the with and without, and in this case we are able to make sure in each of the two trials from where is the sound being generated. Numerical simulation has been carried out as 3D transient simulation. It was performed using ANSYS Fluent software, and it has used the model of F. Wokes and Hawkins in order to estimate the acoustic sources. It has used a turbulence model of large eddy simulations with a subgrid model as kinetic energy transport. Moreover, it has targeted the whole acoustic frequency spectrum from 20 up to 20 kHz, and therefore it has used a time step of 25 microseconds that was calculated according to this equation. Regarding the initialization of this simulation, it has been initialized using data obtained from a steady-state calculation that was performed using a k-omega turbulence model with an SST. Thanks to the periodicity of the flow across the width direction, it was possible to minimize the computational domain by only considering one slice of hills. Therefore, the sheet that was considered in the simulation looked like what is shown in this figure, and by doing so, it was possible to minimize the computational power significantly. After constructing the computational domain, the mesh has been constructed where the domain has been divided into two bodies, body A and body B, and by doing so we are able to introduce mesh refinement in the body A, which is the body of more significance to our simulation. For all the sheets, the body B used the exactly same meshing settings of 3 mm element size, while body A different mesh refinement settings have been used according to the geometry of the sheet. We were trying to obtain the best meshing metrics. Therefore, 1 mm has been used for KMT, maybe 1.5 for the PVO, while no mesh refinement was used for VAB since it had very big geometry compared to the mesh. Then the boundary conditions were established as shown here, where we had velocity inlet and pressure outlet and wall conditions at the higher and lower surfaces, while we used periodic interface at the two sides of the domain. After that, the solution definition has been defined, where we used pressure velocity coupling as simple method for the steady-state run, while we used piezo for the transient run. The discretization of all the physical quantities has used a second order method. Moreover, the transient formulation has also used a second order approach. Now I would like to present the results that were obtained. I will start with the results of the sound pressure level. Here in this figure we have the results from both of the numerical as well as the experimental, and as we can see that the experimental data was higher than that of the numerics. and this may be attributed to the sound reflection, as will be demonstrated in the next slide. Moreover, it's interesting to notice that the difference between the two sets of data decreases as long as the frequency increases. Moreover, also it will be interesting to notice that the experimental data has given sound pressure levels that are higher than the hearing threshold over the whole acoustic range. However, this was not the case for the numerical results, since it gets less than the hearing threshold at the frequency starting from 2 kHz. Moreover, it would be interesting to notice that in the case of the experimental results, no specific sheet can be said to be louder over the whole acoustic range. However, in the case of the numerical data, we can see that starting from frequency of 2 kHz, the KMT sheet, the numerical KMT, starts to show significant loudness over the other sheets. Here I would like to present the data or the results that were obtained from the acoustic camera. As we can see here that the acoustic camera has managed to determine the source of, for example, a 280 Hz sound wave to be emergent from the test section, which is the sound wave that we would be interested in. However, in a different measurement, we were able to see that the sound waves up to 100 Hz has been mainly emerging from the surrounding of the experiment, which referred to the fact that probably the ventilator sound noise is being reflected from the surrounding. Now I would like to go through some velocity contours that were generated from the simulation. The common point among these three contours is that the flow starts as laminar flow, however it changes into turbulent flow across the sheet length. For example, we can see here in the KMT sheet that it was laminar at the beginning, however at the end it was generating vortices, and we were able to see vortices being shed. Again, it was the same case with the VAP sheet, where it is quite turbulent at the end. Moreover, we can notice that, for example, for the KMT sheet, vortices are being shed exactly from the leading edge of the sheet, and mainly from the first hill. However, this was not the case for the other two sheets, the VAP and the PVO, where in the VAP we can see that vortices are being shed over the whole length of the sheet, and for the PVO sheet we can see that vortices again are being shed from the whole sheet length, and it may be more evident here. This may be interesting to remember when we are showing the sound sources in the next slide, where here we can see the contours of sound production locations over the sheets as was obtained from the simulation. For example, for the KMT sheet, it is evident that sound was mainly produced from the first hill. However, for the VAP sheet, it was produced over the whole sheet, mainly from all the troughs, and most, of course, stronger at the leading edge. While in the PVO sheet, it was quite interesting that sound was shown to emerge from the first hill, and then it has skipped the third, fourth, and fifth, and then it started to emerge from the sixth and seventh and eighth hill, which again would be quite analogous to the velocity contours that were obtained here, that we can see that the vortex shedding starts to be stronger from this section. Now I would like to present the error between the velocity results obtained from the two approaches, where error was plotted across the vertical distance of the test section, and as we can see that error ranged from 0 up to 40%, and the KMT sheet has had the highest error. while the web sheet had the most stable error. Finally, I would like to conclude this presentation that in this work we have showed the experimental as well as numerical simulation of the aeroacoustics produced from flow across sheet metals. Some agreements were found between the trend of the acoustic spectra obtained from the numerical and the experimental approaches. However, the experimental data were higher due to the effect of sound reflection. The error obtained between the velocity data obtained from the experiment and the numerical was found to range from 0 up to 42%. And finally, the experimental approach has indicated that no specific sheet is louder over the whole acoustic range. However, the numerical approach has indicated that the KMT sheet starts to be the loudest in frequency above 2 kHz. Thank you very much, and I will welcome any questions. Thank you.